Good day guys, welcome to Calcumind, and today we're looking at normal distribution. So normal distribution is a kind of distribution that occurs in our day-to-day life, from the measuring of height, the measuring of IQ of students, the measuring of different parameters. It usually occur in nature. So normal distribution is being represented with this bell-shaped curve that runs from left to right. So at the center of the normal distribution curve, we have the mean, which is the value. And these other values are deviations from the mean. So if we look at this, it differs from 76, differs from 79 by 2. So this is one deviation away. This is another deviation away. So we can also note that in the normal distribution, 99.7% of the whole values in the table is being contained in three deviations, which is from here, from this point, up to this point. So these are the values contained in the normal distribution. To work out a normal distribution problem, we usually standardize the normal distribution curve, whereby taking the values and converting it using a z table into another value, which is zeros, minus 1, minus 2, plus 1 and plus 2. Is the z table values are being contained from minus 1 down to minus 2, down to plus 2, and we are going to be comparing them using a z table. So we'll be looking at this problem, this past question, which says that a random sample of 6 steel beams has a complete 58,392 pounds per square inch with a standard deviation of 648 psi. Use a level of significance 0.05 to test whether the true average compressive strength is 500,000 psi. So let's explain this question before diving right into it. Okay, let's use a reference. We have an engineer that comes to a company and takes out 6 steel beams from 30 beams. And he was like, the standard deviation is 58,000, sorry, to indicate 58,000, the value is 58,000. And he was like, the standard that we work with is 58,000. And he then tested 6 beams, the compressive strength of 6 beams. And he figured out that their compressive strength is 58,392. It was like, no, we need to go for a callback and test the whole beams in the whole company. So that is not feasible. We cannot test the whole beams in the whole company, their compressive strength. So they took a sample test and they are going to use hypothesis testing to walk through these 6 beams and know whether their compressive strength is greater than 58,000 or less than that. So this is a two-tailed test problem whereby we don't know whether it's above 58,000 or beyond 58,000. So that is when we know that is a two-test problem. For a left tail test, it usually falls below the mean. So we can be trying to compare whether it's less than 58,000. That is when we know it's a left tail test. When it's a right tail test, we usually compare whether it's greater than the mean. So these are the ideas we should keep in mind. So for a right tail test, it's usually greater than, we want to compare whether the compressive strength is greater than 58,000. So firstly, we'll be writing out the hypothesis, whereby HO, which is the null hypothesis that everybody agrees, which is the mean, whereby the mean is equal to 58,000. This is what the engineer says that we agree with. We agree with 58,000 psi for the compressive strength. And he then measures with another external officer, then come to the office and measures. And we figured out that for 6 beams, their compressive strength, which is the alternate hypothesis, is not equal to 58,000 psi. So now we are going to be writing out other parameters that make this equation stand out. So the standard deviation is 648 psi. Our n value, x bar, is equal to This is the sample mean. Our meal, which is the standard mean that we agree with, 58,000. Sample mean, when we say sample mean, is the mean that they tested. So you should just keep that one in mind also. So what again? Our level of significance is equal to 0.05. So now that we have listed out all these parameters, another important factor that we need to keep in mind is z-test and t-test. So when do you know that this is a z-test problem, and when do we know that this is a t-test problem? For a z-test problem, we usually use the values are less than 30. So now we can see how many samples, how many steel beams did they test? 6, which is less than 30. So anytime it's less than 30, we'll be using a z table. But once it's greater than 30, we'll be using a t-test table. So these are parameters we need to keep in mind. So now we'll be converting our values from this z table. We'll be standardizing it from this normal table, in which our 58,000 and 58,392 are present. I'll be converting it to a Z bell curve and comparing it against the level of significance. We are going to be walking through the equation, and I'll guide you on the process. So in order to get our Z value, Z is equal to x bar minus this divided by our standard deviation x all over square root of n. These values on the lower side, in some textbooks, they are usually represented as standard error. So instead of walking through this, they can just write the standard error and you work it out yourself. So this 58,392 minus 58,000 divided by s. Our s is standard deviation all over square root of 6. So if you work out this, what will you get? This will be 392 divided by 648 divided by square root of 6. What do you get? Z is equal to 1.48. So now we have gotten our Z value, and we are going to be doing the test. They say at the level of significance, which is 0.05, using a z-test table, which is a two-test. We are going to be looking at the two-test z-test table. They have a z-test, the left side, and also have the right side z-table. So these are factors we need to keep in mind. We'll be looking at a two-tail z-test table. So at 0.05, the value we are going to be having, at 0.05, the value we'll be having is 1.96. This is the critical value for a two-test table. So we'll be writing it, we'll be indicating it here. If 1.48 falls here in this region, which is falls here, we'll fail to reject. But if it falls beyond this region, we are going to reject it. So we'll call here the reject region and call here the fail to reject region. So now we can see that 1.48, like using a number line system, we'll be able to figure out that 1.48 falls in this region. It's not greater than 1.96. So we'll be able to state out our conclusion that this, we'll fail to reject the assumption that the average compressive strength is greater than this or either less than this. So now we'll state our conclusion. Conclusion is we fail to reject the alternate hypothesis. So this simple conclusion, you can state that at 5% level of significance, there is no sufficient evidence to conclude that the sample, that the alternate hypothesis, mu, is not equal to 58,000. So we don't have significant information to conclude that this our meal is not equal to 58,000. Thank you for watching the video. Make sure to like, share, and comment.